I'm gonna continue from where I left off. It's not really easy to make a pre-recorded video. So, okay, we're gonna calculate the percent error. I select my first value, 315 minus the elastic buckling load, and we're gonna divide it by the measured value. And we have to multiply by 100 to get the percentage. It's 9.7, so the percent error is 9.7 for the first specimen. Let's go down. So we have the negative values over here, but the percent error should be positive all the time. So we're going to use the absolute value. Now we fix the errors. Perfect. If you want to make it better, we can give the number for specimens. One, two, three. So in total we have 9 different specimens. Perfect. So this is how you calculate the percent error. Then we're gonna look at the summary questions. If you already watched my previous video, you should be able to answer the summary questions easily. But let's look at this explanation under the Cullen-Buckland data. In this activity, you will use the tabular data from the Cullen-Buckland experiment and the equations represented in the lecture. That's what we did. We used the tabular data from Cullen-Buckland experiment and the equation that was given in the previous lecture. First, an area moment of inertia must be calculated for each specimen using the area moment of inertia equation for circular cross-section. And the equation can be found in the Cullen-Buckland lecture video or in the previous spreadsheet or in the given spreadsheet. The equation was right here. Let's continue. Second, an Euler-Buckling load must be calculated for each specimen using the Euler-Buckling equation. Pay attention to the end conditions. In parentheses, K of the column specimens tested. That's what we exactly did. So during the experiment, I noted down the end conditions, and based on the end conditions, I select the K factors. For example, in the first one, it was the fixed columns. In both ends, it was fixed, so the rotation and translation were fixed in all directions, as opposed to pin condition, where K value is 1, and the pin condition rotation is not fixed, but the translation is fixed on one dimension. Let's continue. Okay. So the results from this activity should include the table of recorded data from the experiment and the results from EBL, elastic buckling load calculations. You can use the spreadsheet template provided and description of the Cullen-Buckland theory based on the summary questions below. And this section is highlighted. No lab report is required, and all of your work can be combined in one page and submitted in PDF format. Like I said, there is no lab report required in this sections, column buckling experiment, all you have to do, finish your calculations like I showed in this experiment, in this video. Your work should include this table with the results and the description based on the summary question. So let's look at the summary questions. Imagine you're an engineer at a consulting firm tasked with designing a steel column for a simple structure. Your boss requested that you familiarize the design team with the column buckling theory and write a description of the column buckling theory to be used in this project. Things to consider when writing your description should include: first one, what is the importance of the cross-section of the column membered in design? In other words, how does it contribute to the strength of the structural member? Let's look at this. Okay, so we are looking at the cross-section, and I pointed out in the previous lecture how the cross-section affects the moment of inertia and how moment of inertia contributes to the overall strength of the member. So if you increase your moment of inertia, or if you increase your diameter, what happens? It increased your overall strength. Let's look at in this case 0.26. I'm only focusing on this first specimen. So in this case my diameter is 0.26, and I wanna go one size up. Let's say one size up is 0.5. I double the diameter, and we're gonna pay attention to elastic buckling loads. It's calculated based on the given diameter. Elastic buckling loads is 6088 psi, right? So by increasing the diameter, I was able to increase the elastic buckling loads, which is the critical buckling loads of the structural member that I tested. So you can compare this value with the previous one, 445 psi. Well, what about the moment of inertia? Was it increase or decrease? So let's look at the 0.26 again. It decreased. So increasing the diameter will contribute to the increase on the moment of inertia, which will directly increase your member's structural capacity. And you can play with this two examples right here. In one, you have a height of 4 inches, you have the base of 2 inches. You can calculate your moment of inertia if you have rectangular sections, and you can use different cross-sectional areas, shapes. If you look at your mechanics of materials book, and you can find the different sections on the appendices section of your book. So let's look at the second question. What do you think of the moment of inertia you calculated for each specimen? How does it change the strength of the column tested? How it can be optimized? In other words, how it can be increased. So if you have a, let's see, if you have a rectangular sections, you can change the orientation. In other words, if you change the orientation, you change the direction of your member. Let's say in this case your base is 2 inches and your height is 4 inches. Your moment of inertia is 10.66 inch to the fourth. What if I change the orientation and I make the base 4 inches and the height 2 inches? I make the base 4 inch and height 2 inch. What happened? The moment of inertia decreased substantially. So if I have this structural member and I don't want to change the cross section, I want to keep the same cross section, but I want to change the orientation. By changing the orientation, I'm increasing the moment of inertia. So let's go back to the original one, where I have my base and height different values, 2 inches, 4 inches. I have the moment of inertia of 10.66. So this is pretty simple. By changing just the orientation of your structural member, you are able to increase your moment of inertia. You cannot do the same thing when it comes to the circular shaft, because no matter which orientation you use on the circular shaft, you're gonna have the same moment of inertia because of the distance from the neutral axis to the outer fiber is not changing. But it's different when it comes to rectangular sections. This is the reason when you see a beam, say beam moment of inertia deflection, simple. Let's look at the simple definition. Okay, this is exactly what I was looking for, and I just found it. It doesn't matter you're looking at the beam or column. It all depends on the loading conditions. So assuming that we are looking at the beam and I'm looking at the weak axis and the strong axis, we look at the weak and strong axis on the column buckling scenario as well. But you can see the weak axis beam orientation. If you use this orientation, then you're gonna see a lot of too much deflection. But if you use the strong axis beam orientation, then you will reduce your deflection. In the case of column, the column will buckle about the weak axis. So if we have a rectangular section, let's say in our case right here, I have a rectangular section. If I'm using this beam with the cross section, if I'm using this column with the cross section of height 4 inch and base 2 inches, this column will buckle about the weak axis, and it will buckle in and out of the board. Like get it a rectangular shape object between your hands. Make sure it's slender and try to apply a load with your hands, and you will see that this rectangular shaped object will buckle about its weak axis where the width is smaller. In other words, it's the least. In this case, is 2 inches. So by now we know that increase in moment of inertia will result in increase on the column buckling strength. On the third question, we are looking for an answer on the end connections. So how does the end connection affect the column buckling strength? So let's look at these tables again. In the pin column end conditions, we have the K factor 1 as opposed to fixed with the K factor 0.5. And when you go look into equation where the LE or the K factor gets into the game, it's in the denominator. So as the LE, effective length factor, increases, the critical load, the column buckling strength, decreases. So if I have the pin-pin conditions, then what's going to happen is, instead of 0.5, if I put 1.0, pay attention to the elastic buckling load, which is 445 psi right now. It is 113. Automatically, if I change my mind and if I use pin conditions, pin end conditions, if I change the fix to pin, I will reduce my elastic buckling load for this particular member to 111.3 as opposed to 445.2. So you can ask yourself, then why I'm not using, should I use fixed condition, fixed column end condition in my design? One, it is costly and it takes more labor to install fixed column end condition, because in order to provide fixed, you have to restrain the movements on each direction XYZ. So it should be fixed. It should be fixed against rotation and translation in each direction. Fixed beam column connection. So I found the example on my previous lecture. So this is the example that I show for the fixed end conditions. So in this fixed end conditions, let's continue. So if you look at the connections, this beam is secured on his flanges as well as its own web. So you can see the 3 bolts on the flanges at the bottom, and then 3 bolts that's connecting the column to the beam on its web. So it cannot rotate, it cannot translate on any directions. But if you look at the other section, which is the pin connections, you see just only 3 bolts is holding this beam and it's connecting it to the girder on the other side. Even though these 3 bolts it's holding the web, the beam that is connected to the girder, still there will be small movements, and this movement is gonna help to shrink and expand during the hot and cold environments. So we expect to have small movements in the connections, because with the hot weather and cold weather climates, we expect to have some expansion and the shrinkage in the members. So we allow that by using the pin connections. But as you can see over here, it was really easy to finish this connection with 3 bolts as opposed to how many bolts we use? 3, 3 at the bottom to the flanges, 3 in the middle to the web, and 3 on the top, and you have 6 on the other side. You have plenty of bolts and you have plenty of labor that goes into fixed connections. So it's all about the financial reasons and the timing. It is more secure and it is more how can I say, it's more durable when you use fixed connections but sometimes it's not a perfect option. With that being said, we answer the third question. Third question, which was the effect of end condition on the column buckling strength. And the last question, how does the length of the column member affect the column buckling strength? If you look at the equation, you will get the answer intuitively, because the effective length is, or the length is on the denominator. As the length goes higher and higher as you increase the length of your column, which your member starts getting more slender and slender, and your critical buckling load will reduce as you increase the length. Let's say in this case our length was 24 inch, 2 feet. Let's make it 36, and you will see the drop on the elastic buckling load is 197. Let's make it 48, 111. So it's pretty simple.